So for our first talk, it's a pleasure to have Jon Warren speaking to us about reflecting Brownian motions and point-to-line last passage percolation. So Jon, why don't you take it away?
Okay, thank you. Hello, everybody. Thank you for Ivan and the others for organizing this summer of talks. Right. So I'm not too hot on this whole Zoom chat business as well as talking. So I won't be looking at the chat, but I guess, Ivan, you can tell me if there's anything there that I should
yeah, I'll let you know.
Straight away. Yeah. So this talk's based on some joint work with Will Fitzgerald, who was a PhD student in Warwick and is now a postdoc in Sussex. And there is a paper that it's all essentially taken from, which has appeared in PTRF. Okay, so I want to start with a very classic fact, so classic that I have no idea who to cite for this. It must go back at least as far as Levy, I guess, which is about the maximum, the all-time maximum of a Brownian motion with drift. So if you take a driftless Brownian motion, Bt, and a constant mu, and you subtract off mu t, and then that, of course, as a process, the drift dominates as t goes to infinity, and the whole thing goes to minus infinity, which means you have a finite all-time maximum. And that has, very famously, an exponential distribution. And there are many, many ways of proving that. Okay, so what I want to start with is talking about what seems to be a very natural generalization to a random matrix setting of this identity. Okay, so here comes the statement, and then I'll flesh it out a bit in the next few minutes. So on the left-hand side, we've got an all-time maximum of what's going to be a largest eigenvalue of a process evolving in time. And on the right-hand side, we've got some mess, and then EIJs, and the EIJs are independent exponential random variables. So to be a bit more precise, the HT is an n by n Hermitian Brownian motion. So it has entries which are complex Brownian motions. And the drift of our Brownian motion on the previous slide is replaced by t times some fixed diagonal matrix, which has positive entries, alpha 1 up to alpha n. And then we're looking at this process. It's a Hermitian matrix, so for each t, it has a set of real eigenvalues and a largest one, and that's the lambda max. And so then you can look at that largest eigenvalue, and as I'll show in a second, it drifts off to minus infinity because the alphas are positive here, and therefore there is an all-time maximum. And it's equal in distribution to this object constructed on the right-hand side, where, as I mentioned, the EIJs are exponential random variables indexed by points in the integer lattice. And they have rates which depend on the same alphas as we're using in the diagonal matrix. And I wouldn't bother too much about the exact form of those. They'll be familiar to many of you, and if they're not, don't worry about it. And then what we're doing, this construction here on the right-hand side, is a very classic construction. Now you are pi is a path through the integer lattice, starting at the point 1, 1, and ending up somewhere at a point whose coordinates sum to n plus 1. N here is the dimension of the Hermitian Brownian motion on the left-hand side. And these paths, they pass through the integer lattice, and therefore they along that path, you pick up the exponentials with the appropriate labels that lie on the path. And you sum the exponentials for each path, and then you find the maximizing path. And the key thing here is that although the start of the path is fixed at 1, 1, the right-hand endpoint of the path can lie anywhere on this line here of coordinates who sum to n plus 1. So when you take n equals 1, the left-hand side degenerates to just the all-time maximum of Brownian motion with drift. And the right-hand side, the path is degenerate because the only box that it can pass through is 1, 1, and then it's finished. And so you just get E11 on the right-hand side. So this is then exactly the case on the previous slide. So a couple of diagrams, pictures, roughly drawn pictures to illustrate this, the objects that we're talking about. So this is the eigenvalues of the Hermitian Brownian motion with drift. This is a process in T. I've drawn it with n equals 3. So there are 3 eigenvalues evolving in time. They are, this is the Dyson Brownian motion, if you like. That's the, it's a diffusion, in fact, a 3-dimensional diffusion if n is equal to 3. And the 3 eigenvalues start together at 0. My H0 is the null matrix, and they push each other apart. And as t goes to infinity, the t times d, where d was the fixed diagonal matrix, dominates, and it drives all of the paths to minus infinity at rates which are the alphas, in fact. Okay, so because of that, the top path in particular goes to minus infinity, and there's a maximum, and that's the random variable on the left-hand side of the identity. On the right-hand side of the identity, well, this is a pretty standard description of what's called last passage percolation with exponential data. So I've drawn, this is n equals 3 again. I've got some boxes which represent part of the integer lattice, and in the boxes I've got these independent exponential random variables. And then I have paths that start here in the box 1, 1, and they have to end in one of these 3 boxes on this diagonal. So in fact, if I counted right, there are only 4 possible paths in this setting. And for each one of them, you sum the appropriate exponential random variables. So you get 4 sums, each of 3 of the exponentials, and then you take a maximum. And so the statement is that these 2 slides are describing a random variable which has the same distribution. So one approach to an identity in law is always to just compute the distribution of each side of the identity and then check that they're equal. So the point to line last passage percolation that was on the right-hand side of the identity, when the case that the alphas are equal, in fact has a very nice distribution, which is itself a random matrix eigenvalue. It's the distribution of the largest eigenvalue from the Laguerre orthogonal ensemble. And the Laguerre orthogonal ensemble usually has 2 parameters, an m and an n. And I've just written n here because the other one is n plus 1. Okay? So it's a particular case of the Laguerre orthogonal ensemble. And that's a result that goes quite a long way back, at least Bike and Rains, I think. Now, what have we got next? So there, of course, there's also, I should say that there's a lot of other work in the literature on this random variable, this last passage percolation time, point to line with exponential weights. It appears in work on the TASEP with periodic initial conditions. If you start the initial conditions with the spacing, I think being 1 particle, then a space, then 1 particle, then these point to line last passage times actually describe the times for particles to move certain distances in that model. And then there's also some recent work which is by Nikos and Elia at BC on point-to-line polymers, and I'll mention polymers a bit later, which includes calculating the distribution of this in a new way. So there are certainly calculations of the distribution of the right-hand side, and on the left-hand side, the result in the literature that first made Will and I realize that there might be a connection was that you also get an LOE distribution the largest eigenvalue of the LOE arising in a situation where you have non-intersecting Brownian bridges. So this is a little bit like the random variable I had, but it's not quite the same. These bridges here, they all start from 0 together, n Brownian motions, and they push each other apart, but then they're conditioned to all come back. That's why they're called bridges at time 1 to 0 again. So this is also sometimes called a watermelon. And if you look at the maximum of the top particle in the watermelon, the highest particle, over the time interval, and then square it, you get this LOE distribution. So you get an identity between these two random variables in distribution, therefore. There's a fairly straightforward way of going from bridges to Brownian motions with drifts. And if you apply that to the right-hand side here, the square disappears and you get the special case of the result I showed you with the Hermitian Brownian motion with all the alphas equal to 1. So that gives you one proof of the theorem, right? By combining these two results and making that transformation of these bridges into Brownian motions with drifts. Right, so next slide. So this is a representation of this largest eigenvalue that we're interested in, which is going to be important to us. And it's quite surprising, right, that this largest eigenvalue as a function of t is not a Markov process, because it's only part of an n-dimensional Markov process. But it can be built in quite an amazing way from a sequence of independent Brownian motions. So here I'm going to, and actually throughout, I'm going to use B subscript minus alpha to denote a Brownian motion with drift minus alpha. And here in this sum, you've got n Brownian motions, B1 to Bn, whose drifts are given by the alphas, and they are taken to be independent. So one way of tackling the left-hand side of the theorem that I stated is we want to take a supremum over all time. So that means we could take this expression here and take an additional supremum over t, because it's an identity that's not just true at a fixed time, but it's an identity that's true as processes in t, okay? So that means you can take a supremum on both sides with respect to t, and that actually just adds one extra supremum on the right-hand side. So that's the right-hand side. I mean, is a rather wonderful expression, even if it's a bit intimidating at first. You can interpret it as a system of Brownian particles reflecting off each other. I should mention that I think Baryshnikov is usually cited as being responsible for the result for a fixed t as an identity in law, and it's O'Connell and Ure that prove it as a process in t. Another way of thinking about the right-hand side is that it's a last passage percolation time itself, only instead of having an environment which is exponential random variables in boxes, it's white noise on a set of n line segments, each running from 0 to t. I'm just saying that as an aside, really. So let me just pause and say something about identities and proving identities in law, right? I mean, so on the Prass side, essentially we proved, I gave you an argument for proving the identity in law we're interested in, at least in the special case that the alphas are equal to 1, by just combining a statement about the distribution of one side, identifying the distribution of one side, and then identifying the distribution of the other side and checking you've got the same distribution. And I mean, that's a strategy you can always adopt for an identity in law. It can be the case that you can compute the distribution of the two sides and get formulas and then have an issue with checking that actually it's the same distribution because your formulas don't match. So that certainly happens, actually, that although both sides can have distributions you can compute, you can end up with expressions that are not obviously equal to each other. And then there can be a problem in doing that. But I think very often those are not sort of satisfying proofs. And a more satisfying proof for an identity of law somehow tries to relate the two random variables themselves that appear on the two sides of the identity. So there's always an issue with, can you find a construction which somehow relates the random variables rather than just their distributions? And if you look at this formula here at the top of the page for the largest eigenvalue involving n independent Brownian motions, and you bear in mind the classical result that I started with, which was that the maximum of a Brownian motion with drift is an exponential random variable, then what you should feel you would like to do is find the EIJ random variables hidden in these Brownian motions appearing on the right-hand side at the top of the page. So we tried to do that and failed. My hunch is they're not there, but it would be interesting if somebody else proves me wrong about that and does find them there somehow.
I guess for n equals 1, it's there, right?
Well, almost tautologically, because I'm saying that the way in which you would hope to find an exponential on the right-hand side is as the maximum of a Brownian motion. Yeah. So if you've only got one of them there, and you've got the exponential, yes. But so you might think maybe the all-time maximums of some of the differences or something constructed from the differences somehow generates the EIJs. But I don't think we couldn't find a way of making that work. I mean, I think if you'll let me make one other comment about identity in laws. I think one thing that happens that's always worth bearing in mind is that sometimes there can be absolutely no relationship between the random variables on the left-hand side and the right-hand side of an identity in law, and they just happen to have the same distribution. And I think that happens because if you're looking at nice random variables in nice models, then you hope to get nice distributions. And that certainly happens with integrable probability, right? And then there aren't all that many nice distributions to go around. So somehow by the pigeonhole principle, sometimes you'll get random variables in different models that end up having the same distribution, and there's no relationship between the models and the random variables. It's just that, there weren't enough different nice distributions for them to end up being different. And I think that does really happen, right? Anyway, my claim is that somehow what's going on here is a bit between these two extremes. You can't find the EIJs in the BIs, or I couldn't, but you can try to relate what's going on the two sides of this identity in law in a bit more of an interesting way than just say it's a fluke. Right. So this is a bit more classical first course in Brownian motion type stuff. So let's go back to just thinking about one Brownian motion with drift. And I'm going to define a new process, yt, and it's the maximum from 0 to t of the Brownian motion with drift at time t minus the Brownian motion at time s. And if you rewrite that by just pulling the bt out of the supremum, then you get it in a form that maybe is a little bit easier to think about. It's the height of the Brownian motion above its minimum between 0 and t. And therefore, when you let t vary, what's going to happen is the y is going to track this b, except when this b reaches its minimum. And if you think about that a little bit more, that tells you that the y is evolving as a Brownian motion in the half line with a wall at the origin. Every time it tries to go negative, when y is 0, the right-hand side is 0, bt is at its minimum, and it can't go negative. And that is because there's a sort of kick up which pushes it non-negative again. Okay, that's Levy's, Levy's scorecard. Now, the reason I wrote my yt in this form here as the first expression with the supremum in, is that I want to do a time reversal argument. So if you fix a t, and you look at this process bt minus bt minus s, then that's the Brownian motion basically run backwards from wherever it ends up at time t. And it is, of course, in distribution as a process in S, a Brownian motion. Okay? That's the time reversibility of Brownian motion. Now, if we go to our expression up here for yt, and you just replace s by t minus s, which you're allowed to do in the supremum, that doesn't make any difference, then what you've got here in brackets is exactly the Brownian motion run backwards expression from here. And so you get that yt is equal in distribution for a fixed t to the maximum over the time interval 0 to t of the Brownian motion with drift. Okay. Yt is a reflected Brownian motion, a Brownian motion with a wall. This is just the maximum of a Brownian motion to time t. They're not at all the same thing, but they have the same distribution at any time. Fixed time t. If you send t to infinity, then this maximum over the interval 0 to t turns into an all-time maximum. That's obvious, right? Because as t increases, this random variable is increasing. Okay, so there's nothing fancy there. That's happening almost surely. And then that we said had the exponential distribution. So what you've just done there is seen that the stationary distribution of the reflected Brownian motion with a wall is exponential. And that's a very classic little bit of probability, which is also goes back a long way, and I don't know who really must have first realized you could do that sort of time reversal argument. It's certainly applicable in queuing theory for the MM1 queue, where you're working with Poisson processes instead of Brownian motions.
But John, is it really, so it's the stationary distribution, but it's more than that, right? Doesn't yt actually converge to a single exponential?
Well, it does in distribution, but y is a Brownian motion bouncing off a wall, so it doesn't converge in any stronger sense than in distribution.
I see. Okay.
Yeah. So that's what's clever about this. These two, in this identity here that I've got down here, on the left-hand side, as t varies, yt bounces all over the place. But on the right-hand side, things are increasing. So proving there's a limit on the right-hand side is trivial. And that gives you the stationary distribution of y. Right, so that's my sort of second classic fact, if you like, that a Brownian motion reflected off a wall at the origin and with a drift towards the wall has an exponential stationary distribution. Now, here's a more complicated system of reflected Brownian motions, which are going to be built from a sequence of independent Brownian motions, Bj, all of which have drift. So y1 is the same thing as yt that we've just been looking at. That's a Brownian motion that's pushed upwards from 0 every time it tries to go negative. And then we iteratively construct some further processes, y2, y3. Each are driven by a new independent Brownian motion with drift, but there's also the previous y appearing in the formula. And let me just rearrange things slightly. Well, if you, I don't know whether you'll follow this on, but anyway, if you look at the difference, yj minus 1, so that means you need to take this formula here and put a yj minus 1 of t into it and rearrange it, then you can make it look like what we were looking at in the previous slide, right? So it's this process, bj minus yj minus 1, minus its previous minimum. And that shows that it's always greater than or equal to 0. So what you're seeing there is that each yj is always bigger than yj minus 1. And it's not very surprising to see, I mean, as t varies, this is the Brownian motion that's driving the left-hand side, okay? So that must be driving the yj, but then there's a push when this is equal to its minimum. And that's the push that pushes yj up and prevents it from going below yj minus 1. Here's a picture, okay? So the yellow thing is my y1. That's simply a Brownian motion with drift towards the origin that gets pushed every time it tries to go negative. So along the time axis there. And then the green process represents a Brownian motion, which is trying to do an independent thing, okay, because it's driven by a B2. It also has a drift towards the origin. It's pushed whenever it tries to go below the yellow Y1, okay, and so on and so forth. Everybody's got a drift towards the origin. This is a bit of a bad diagram because it sort of looks like things might be tending off to plus infinity as t goes to infinity. It's not. They're going to come back down to 0. And you shouldn't really be surprised that this is I mean, it's obviously a Markovian evolution in time, and it's going to have a stationary regime. It's going to settle down to some stationary regime, okay? And it's that stationary regime that I'm interested in. We know that under that stationary regime, Y1 has an exponential distribution. We've already seen that. Well, so I'm not going to go through the time reversal argument, but in detail, but basically the calculation we did with Y1 that showed that it had an exponential invariant measure can be generalized. You take your formulas for Yn and you do the same sort of time reversal of all the Brownian motions that appear in them, and you get exactly the O'Connell-Ure representation for the maximum eigenvalue of the Hermitian Brownian motion, only with the extra supremum that you wanted. So this first identity here is basically the same argument as we just did on the last slide, but 1 for Y1, and it all works the same way. Now, as t goes to infinity, this supremum increases to the all-time maximum of the largest eigenvalue. So that's the random variable we were interested in. So what you've got there is the fact that the Y process of the system of reflected Brownian motions with a wall has a stationary distribution such that the top guy, the highest guy, Yn, the nth guy, if you like, under that stationary distribution has the same distribution as the random variable that we were interested in from the beginning of the talk. Okay. So that sort of makes the Y process an interesting process, I think. Okay. Yes, so that, just to reiterate, so the stationary distribution of the top particle of Y is equal to that of the all-time maximum of the largest eigenvalue of the Hermitian Brownian motion. So just to remind you of what we already know, which is that if Y is stationary, then at any time t, this Ynt has the same distribution as the all-time maximum of the eigenvalue of the Hermitian Brownian motion, which when the alphas were all equal to 1, turned out to be essentially the largest eigenvalue drawn from an LOE, Laguerre orthogonal ensemble. Okay, so that means that if you send n to infinity, so you've got Y1 and then Y2 on top, Y3, then Yn appropriately rescaled. Well, these LOE Laguerre orthogonal ensemble eigenvalues are converging to the Tracy-Widom F1 distribution. So that means that the Yn is in distribution converging to the Tracy-Widom F1 distribution. And then it's quite natural to ask about what happens if you take 2 times Yn at T1 and Yn at T2. So this is a sort of problem that's arisen quite a bit in the literature for other processes. And it looks like you've got the right sort of structure here to be able to do something with this. There are formulas for the entire stationary distribution of Y. And then there's a formula for the transition density of the process Y as well. So you put those two things together and you're going to get the joint distribution of the whole of y1 up to yn, the vector at t1, together with y at t2. And then you just have to integrate out the variables you don't want, which are y1 up to yn minus 1 at t1 and y1 up to yn minus 1 at t2. And the formulas are full of determinants, and you expect that you can maybe massage these determinants into some sort of Fredholm determinant which describes the joint distribution of the yn at the two times. And then you might hope that as n goes to infinity, well, you want an extension of the F1 distribution to multiple times, and that's an object that's defined and understood. It's the area 1 process. So here's a conjecture, right, which is that the top line of this reflected Brownian motion with a wall converges in distribution as a process to the area 1 process. Now, we tried to do this, and although I said we've got the right ingredients in the sense that we've got formulas for the stationary distribution and the transition density that will take you from T1 to T2, and they're all a nice determinantal form, we couldn't make the sorts of arguments that have been used previously to derive Fredholm determinants in that setting work for these specific. The wall seems to make a difference, and we couldn't get it to work. Now, that might well be just because we weren't up to the job, or at least I wasn't. I should leave Will out of it. So we sort of put that on one side and gave up on it. But let me make an additional comment that seems relevant now, or more recently, right? So, big breakthrough of the last year or so has been the construction of something called the Airy sheet, which is a 2-parameter process. Those of you who sort of know what it is, fine. I don't suppose it's probably not worth me trying to explain now when I can't even draw anything. And the paper that constructs this by Dufresne, Altman, and Virag, it's coupled to an infinite sequence of Brownian motions. The S, which is a fantastic object, comes associated with, coupled, living on the same probability space, I think, even as this sequence of Brownian motions, B1, B2. And if you look at that coupling, then, and you look at the formulas that we had for Yn in terms of the Brownian motions we built it out of, the Brownian motions with drift, then what you see quite easily, immediately really, is that the YNT as a process, so the top line of this system of reflected Brownian motions, is converging in distribution to something that you can build out of the Airy sheet, which is that you take your 2-variable sheet and you take a supremum over the y, the second variable, and then that leaves you the x free. And so x here is the parameter of a one-dimensional, a one-parameter process, and that matches up after a bit of rescaling with the t, that is the time parameter in the YNT. So, I mean, the whole idea of the Airy sheet is such that one would expect this guy, this thing with the supremum, to be the Airy 1 process. And so that then would give a proof of the conjecture. So the thing I don't know, and this looked like a good place to ask it, because I'm not up to speed with what the state of the art with the directed landscape is this thing, the sup over y, sxy, already known to be the Airy 1 process, identified as the Airy 1 process? Of course, it should be, but is that proved? If it's not proved, then going back to my previous, being able to do this calculation and take a limit as n goes to infinity would give you a proof of the fact that this was Airy 1 as a process in X. So either I'd like to know that this is already known, or I leave it to you as a reason for why you should be interested in Y and T at T1 and T2.
I guess the only reason why that wouldn't be known is that the construction they use is through the sort of Brownian last passage percolation, right? Where the notion of this point to line is a little bit more convoluted. And I don't think they've done it yet directly for like exponential or geometric LPP.
Yeah, yeah.
So maybe it's not known exactly, because I don't think anyone has. Well, actually, maybe people have done point to line in the case of Brownian LPP. There was something Herbert Schwann did with a master's student a few years ago. I think he was working on something of that type. So it might, but it might not. So I don't know.
So that's, let me move on. Yeah. The YN, we've just been talking about looking at the top particle in the system and letting T vary, okay? So now I want to do the other thing that you can do, which is to fix a T and for the stationary process. So you're just looking at the invariant measure and look at all the particles, okay? And so what's nice here, and shows you that there's more going on in terms of the connection with the last passage percolation with exponential data, is that the entire stationary distribution here can be described by a vector of last passage percolation times. So the indices are going to do something a bit weird, but maybe I should first of all give you the formula. So this is the same last passage percolation, point to line, as we were talking about before, basically, with exponential data and paths through the integer lattice. And these paths are all ending on the line I plus j equals n plus 1, somewhere. What's slightly different is that rather than starting them at 1, 1, you're now starting them at other points, okay? So when k and l are each 1, then this is exactly the last passage time that we appeared in the first result. But in general, what you're doing here, so that's the G11, then that's the same last passage time as appeared in the first result, and that matches up with the YN, so the marginal distribution of the top particle under the invariant measure. And on the other hand, G1n, well, 1 plus n is already n plus 1. So G1n, you're already on the line. So your pi is then a trivial path that just picks up one box. And that's one exponential. And so G1n is an exponentially distributed random variable. And that is, of course, the marginal distribution of Y1. And then the point is that as you move where you start from, you get the whole vector of last passage. Well, you build a vector of last passage times that then gives you the stationary measure of the reflected Brownian motion. So let me just point out, if you proved this, if you had a proof of this, this would then imply the first result, right? Because it's just a special case that Yn has the distribution of G11 then. Right. So, oh, right. So now apparently another bend in the narrative. I'm going to talk briefly about finite temperature setting. So here's another classic result, which you should think of as comparable to the statement that the maximum of a Brownian motion with drift has an exponential distribution. This does not go back completely into the mists of time. Instead of the maximum of a Brownian motion with drift, you're looking at the integral of the exponential of a Brownian motion with drift. And the distribution that appears is the reciprocal of a gamma variable. And that's known as Dufresne's identity. Now, I want to emphasize that that's an analog of the statement that the maximum of a Brownian motion with drift has an exponential distribution. And there are analogs of the other objects that we've seen in the story as well, right? So if instead of just looking at a supremum, an integral, you look at this object that I'm calling ZT, which is the exponential at time of the Brownian motion at time t, and then an integral from 0 to t of the exponential, and now there's a minus sign that appears, then that turns out to be a diffusion. And that's an analog of the reflected Brownian motion with a wall at the origin. And our time reversal argument works again. So just exactly as I showed you that the maximum of the Brownian motion with drift being an exponential was related to the invariant measure of the Brownian motion with a wall, then what happens here is that if you do the time reversal trick in this expression for ZT, then you see that ZT is equal in distribution. So you're just replacing, you're bringing that exponential inside the integral, and then you are replacing S by T minus S, and then using the reversibility of Brownian motion. Then you get that ZT has the same distribution as this integral from 0 to T of the exponential of the Brownian motion. And as you send T to infinity, that turns into the infinite integral, okay? Because there's nothing inside the integral that's varying with T. So that convergence as T goes to infinity is a trivial one. And then we've said that this infinite integral has this inverse gamma distribution. So that tells you that the diffusion that you've built here, it's easy to check it's a diffusion, just use Ito's formula on the right-hand side. I'll show you that in a minute. That shows you that that is converging in law to the inverse gamma distribution as T goes to infinity. So its stationary measure is the inverse gamma. Actually, I think typically this argument is used the other way around. What you can do is you can prove this identity I started with by checking that inverse gamma is an invariant measure for this diffusion Z, okay? And then that tells you that this identity at the top of the page holds, Dufresne's identity. So there's the statement. Oh, wow. So now all I'm doing is putting a parameter beta in, which of course is familiar to most of you. It's just appearing in front of the Brownian motion. And then if you take logarithms of it, then here's the, so actually I said that Z was an analog of the reflected Brownian motion. It's not quite, it's log that's the analog of the reflected Brownian motion. Because when you take the log and you do a bit more Ito's formula, then what you get is that you're getting the B is the driving Brownian motion, and then you get a drift term, which is essentially e to the minus y. So you get a drift when you go negative that pushes you back to being positive. And if in the parameter beta tunes the strength of that drift, and if you send B to infinity, then this guy rather obviously converges to a Brownian motion with a wall at the origin that it gets pushed up from, okay? So that means that we can look for an analog of the previous results in this sort of exponential setting, and that works fine. So here's the statement. So you form a multi-dimensional integral of exponentials of differences of Brownian motions, and this should make you think about the O'Connell-Ure representation of the largest eigenvalue. Essentially, this is an analog, this expression here, to the O'Connell-Ure representation of the largest eigenvalue, except that we've got an integral over the last variable Sn, and that's the supremum over time of the largest eigenvalue. So there's an extra integral there that you might not have, but that plays the role of that supremum over time. And then that's equal in distribution to something that's built out of inverse gamma random variables in an analog of the way in which the last passage time is built out of exponential random variables. All that happens is that instead of summing over paths, we take products over paths. And then instead of taking a maximum over paths, we take a sum over possible paths. So that's then what's known as the log gamma polymer. And the pi is the same, has the same constraints as before. It starts at 1, 1, and it ends somewhere on the line I plus j equals n plus 1. Okay. How are we doing for time? Are you going to get, let me keep
10 more minutes.
Yeah, okay, good, thank you. So let's park that exponential stuff for a minute. I'll mention it right again at the end. And go back to reflected Brownian motions, where the interactions are sort of local. And I want to go back to my YT, which was this sequence of Brownian motions, one bouncing off a wall, then the next one bouncing off that one, and so on, right? And I want to make it into an even bigger, more complicated object, where instead of being just a vector, well, it's a bigger vector, because now I'm going to have processes Yij with two indices, so indexed by points in the integer lattice. And I'm going to write down some equations that look awful, and then I'm going to draw, and then there's going to be a picture on the next slide that will explain quite how these Y's are. So the thing to think about is in the last passage percolation setting, you've got the integer lattice. I had those boxes that had exponential random variables in, okay? And now I want you to think about there being one of these Yij's, which is a process depending on t, sitting in each one of those boxes, okay? Now, along the first row, so taking I equals to 1, then these Y's, Y1J's are just doing Brownian motion with a constant drift, and then a impulse term, which when I get to the definitions at the bottom is going to mean that they push, each one pushes the next one along, okay? So this actually is going to turn into a copy of my previous vector YT, okay? So that's easy. Then the question is what happens for Yij where I is not 1? So this is the equation for the other Yij's, and you get a new Brownian motion. These B's are all independent of each other as you vary I and J. And now the drift term is no longer constant. It depends on your relative position to one of the other Y's, okay? If you're smaller than this particular Y of interest, then you get one drift, and if you're bigger than this particular Y of interest, you get another drift, okay? And now there are two local time terms which are going to keep this Yij in the certain position relative to the other Y's. So let me fill in a few more details. These Yij's, this is defining the L's as local times of certain differences, but I think it's easier to see the interactions between the Y's by drawing a picture. So here's the picture. Now, for reasons that I forget, we flipped the things about the diagonal, unfortunately. So in my last passage percolation picture previously, my boxes were all below the diagonal line, right? And with the boxes containing the exponentials. And what I want you to do is mentally imagine flipping the boxes so that they're all above the diagonal line, okay? But the exponentials aren't there. Instead, we've got this Y's sitting in integer lattice positions, and they're satisfying that system of SDEs that I had on the previous slide. And the various lines on this diagram are telling you how the Y's are interacting with each other. So this first arrow here just tells you that Y14 is pushed away from 0, right? The only impulse is the one that keeps it above 0. So that is in fact an ordinary reflected Brownian motion with a wall at the origin. And then this Y13, the only incoming arrow is from Y14, and that's telling you that this Y14 pushes Y13 up whenever Y13 tries to go below Y14, and so on, right? So the top row here in this picture is exactly a copy of my Y process from earlier in the talk, okay? Each one is driven by an independent Brownian motion. They've each got a constant drift, and the only interactions are the ones that keep them ordered. This bigger than this, bigger than this, bigger than this, bigger than 0. Right? Now, the next row down, things are a bit more complicated. So y23 is pushed away from 0 again, right? So it sees a wall at 0 and it's pushed away from that, keeps it non-negative. It's also pushed down by y13, this random variable. So it has to always be between 0 and whatever y13t is, okay? Everything's evolving in time. And so similarly, right, if I pick y22, that is somewhere between the value of y23, which lies below it, and y12, which lies above it. And it's kept in that relative position by impulses that push it down and up if it tries to get out of that interval. And then the line with the squiggly line, diagonal line, is the thing that tells you that the drift of y22 depends on its relative position to y13. Okay? So it's quite I suppose it's a fairly complicated system of interacting Brownian motions, but it has the nice property that the top row is our previous y process. Okay? So now, this extends the previous result. What's nice about this huge field of y processes is that it has an invariant measure, and its invariant measure is exactly the distribution of the last passage times, which are all point to line, okay? But the point you're starting from is varying. So the GIJs are actually, if you now imagine exponentials living in this picture as well, and then the G11 would involve the last passage time from 1,1 through to this line. G12 would be the last passage time from here through to this line, somewhere on this line, and so on, right? So this theorem implies the previous theorem, which then implies the first theorem. Okay? Because, I mean, if this huge Y family has this invariant measure, then the top row has the invariant measure of the top row of the G's, if you like, and then that was the statement of the previous theorem. Okay, and then Y11, which is this guy, has the distribution of G11, which was essentially equivalent to the theorem I started with. So, yeah, okay, that's just defining the GKLs as last passage times with varying starting points. And I think maybe Ivan's going to leave me one slide to show you, tell you how you prove this last theorem. Ivan's going to give me enough time, I hope, to just for this one slide.
Sure.
Which is that you write down a formula for the joint density of this whole field of last passage times, point to line last passage times. And the key thing there is that it's an elementary formula. So last passage times, you know, are serious objects with complicated distributions, except when you look at them all. When you look at them all, then basically it's not, the point being you can recover from the whole field of last passage times, you can recover the exponentials. And the joint distribution of the exponentials is just a product measure. And so it's actually very easy to use that fact to write down the joint distribution of the whole field of last passage times. The whole problem is marginalizing because you don't want all the G's, you only want ultimately G11. So you've got, you end up with a very elementary formula for the proposed invariant measure of this system of reflected Brownian motions. So you just have to check that that formula is invariant for the dynamics you've described. So you write down the generator. Well, I pretty well have written down the generator because I wrote down all those SDEs. And then you try to check that the adjoint of that generator applied to this formula you've written down for the joint density of the G's gives you 0. So there's a fly in the ointment there, which is a technical thing, which is that the discontinuities in the drift and the local time terms that are the interactions between the particles, they're a bit iffy. I mean, in the sense that multidimensional reflected Brownian motions should be treated with a little bit of caution. You need to be careful about things like exactly what G star is and what its domain is. So you can circumvent being careful because what you can do is switch to the exponential version of things, where you look at a log gamma polymer, and you replace the Yij's by Brownian motions with exponential interactions. So basically, it's very similar dynamics. The formulas are just a bit more complicated because they've got exponentials instead of local time terms in them. And then checking G star rho is equal to 0 is just sort of involves doing things locally on the integer lattice. And so this final check is fairly straightforward. And then, of course, you've got a parameter beta, which is the inverse temperature, and when you send it to infinity, it turns into the reflected system you're interested in the last passage times, and that gives you a proof. So, yeah, and then that proves all the theorems that I've presented. Okay, thank you very much.
Thank you very much, Jon. Yeah, I know the applause is underwhelming on Zoom.
Especially when you've muted yourself.
The talk was very nice. So maybe we have time for maybe one or two quick questions. If anyone has, maybe I have one to begin with.
It's 4 o'clock.
So you spoke about the the exponential model, but of course there's geometric last passage percolation. Does this have anything to do with random walks and maxes of drifted random walks? Is there some sort of discrete version of any of this?
Right. So the short answer is that you can do in a Schur setting, which would be the random walk equivalent of the last passage percolation problem. Then Will has done the calculations in the last few months, actually, and he's got some very nice results, and it all works as you would hope. That's part A of my answer. Part B of my answer is if you try any harder, so what would be the next thing to look for? Maybe something involving Q Whittaker, so a finite temperature model, discrete model. Then so there's certainly we haven't done anything. I've thought about it. Will thought about it. It looks like there's some interesting obstacles. So one thing is that the time reversal step, that famous time reversal thing that relates the invariant measure of a reflected Brownian motion with a wall to the maximum of a Brownian motion. I don't know what the Q Whittaker version of that statement would be. Even with just sort of one particle and a wall, right? And it may be that it's not. There might be something subtle there going on, which is related to the fact that the RSK algorithms for Q Whittaker are randomized. So rather than the time reversal being in a deterministic transformation, maybe there has to be some sort of coupling involved between the sort of forward version of the process and the backwards version of the process. So I think that's a good question, and I would love to know how to do that, if it can be done, in fact. It's always possible that there isn't a Q Whittaker version of that time reversal step, but you would think there was something.
Right, thanks. Any other questions now? Okay, so let's all thank Jon again. And the plan is there's a different room for Nikos's talk. Sorry. So I'm going to close this. I just put the link, or you can find it on website or email. I'm going to close this session and then immediately join the next one, in which Nikos will give a talk on related subjects, in particular RSK. Okay, I'll see you all in a moment.